Okay.
Good morning, everyone. Today's talk will be given by my close collaborator and friend, JB Nation, emeritus professor from University of Hawaii. And we're very, very glad to have JB with us today. And he will be giving an interesting talk on something he was involved recently, and this is plane geometries from vector norms and the Pythagorean theorem. Please, JB, the floor is yours.
Thank you and good morning here. I know it's not morning there, but at any rate, I want to talk about something on elementary geometry. And one of the themes will be that we will use only things which you have taught in undergraduate mathematics. Okay. So, but a combination of a number of those. And except for what you learned in high school. Okay. Uh, Preliminary, let me say that I don't hear very well, and you may have to type questions in chat rather than just sort of me listen to them. Okay, let's begin. Oops, get this thing to click. There we go. So you know the Pythagorean theorem. Pythagorean theorem is that if you have a right triangle in a Euclidean plane, then a squared plus b squared is c squared, where c is the hypotenuse opposite the right angle. And you know several proofs of that. In fact, there are hundreds of proofs. And well, let me just remind you of a couple. One, of course, is one of my favorites is to take a square, which is a plus b by a plus b, and then you look at the interior square and just take the area, and you get a plus b squared is c squared plus 4 times the triangles. And so that's a simple proof. This uses the notion of area. So actually a more elementary proof is the following, which is also an easy proof. Namely, you take a right triangle, this is a right triangle up here in the corner, and you drop a perpendicular to the other side, and then you have three similar triangles, the one on the left, the one on the right, and of course the original. And what does this use? Well, not a whole lot, except that the sum of the angles of a triangle is 180 degrees, a straight line. And that remains true even in the more general models that we're going to discuss. And that these right angles, of course, are all the same. That does not remain true in the more general models. So anyway, then you look at the proportions and you get this proof. The motivation for the investigation is two new proofs, in fact, several new proofs, found by two high school students in New Orleans in December of 2022 as a class assignment. And the proofs were really quite inventive, but raised a lot of questions. First of all, the news reports were not very accurate. And so you had some questions as to what was going on, and it took a while to straighten that out. And so I asked myself, can you trace the Pythagorean theorem back to its source? This, by the way, is my daughter going back to the source of one of my favorite waterfalls on the island of Oahu. And I was there just a couple of days ago, but there wasn't much water. It hasn't rained a lot. Okay, so we know that, in fact, knowledge of the Pythagorean theorem is quite ancient. This is one of the cuneiform tablets that has a problem involving the Pythagorean theorem. And so here's a brief history of geometry. maybe not totally complete, but the Babylonians in about 1800 BC had a pretty good working knowledge, and there are a number of tablets which they understood how the Pythagorean theorem worked, and also Pythagorean triples, which they had a particular interest in. And then other ancient societies, Egyptian and Chinese and Indian, also developed an understanding. So certainly it was well known. But there's a big change with Euclid's Elements about 300 BC, in that there's an axiomatic approach, not just about areas of land or areas of various things, but actually understanding how geometry works, not just Pythagorean theorem, but all of geometry. And this is a sea change, you know. Well, the elements were not perfect. For some notions, for example, betweenness were not very well described and used into geometric intuition. So we'll skip a few people until we get to 1899 with Hilbert's Grundlagen Geometry, which tried to refine and get a really good set of axioms which would not be dependent upon your geometric intuition. And this, again, is a big change, although not in spirit, but in actual things. But it was less than perfect as well. And different people refined this in different ways until we get to the recent book by David Clark and Samrat Pathanea, a full axiomatic development of high school geometry. And so this can be thought of as a culmination of about a little over a century of refinement of Hilbert's ideas. And there it is. So I'm suggesting you go out and buy multiple copies. It's actually really a great book, except it doesn't have all the proofs in it, but because it's been as a textbook. At any rate, so here's the features. It starts with the basic notions of a plane being a set of points with a distance function, and those are the only primitive notions. So everything else, lines, circles, angle measure, area measure, are developed from simply points and lines. And then it has a set of 10 Hilbert-style axioms, some of which have several parts. And so you'll see me refer to different parts. And develops the entire theory of Euclidean geometry from those axioms, which of course is what Euclid was trying to do and what Hilbert was trying to do. But this is a modern refinement of that. And again, not the only one, but probably the most recent and sort of the pinnacle of achievement, at least till now. And it proved that the only models of these axioms are when you take the field to be a Euclidean field, so an Archimedean field in which you can take square roots. You're going to need square roots for things like the Pythagorean theorem, okay? And then just the normal distance, the square root of x squared plus y squared is the distance. Up to isomorphism, these are the only models of the 10 axioms, okay? And of course, in particular, the Pythagorean theorem is true, and you can prove it. So let's go through the axioms, okay, or actually the definitions. So a point Q is between P and R if the distance from P to R is just the sum of the distances from P to Q and Q to R. And instead of 3 or more points with this property, one of them between the other two is a straight line. And then a circle is defined as always, a set of all points a given distance from a center. And isometry is what plays the role of automorphism of the plane. That is, it's a mapping which maps the points and preserves distances. Now, ordered subsets are congruent if there's an isometry that takes one into the other. The only caveat here is that these should be regarded as ordered sets. So, for example, the triangle ABC is not the same as BAC, okay, because you look at the order of the vertices, and you say isometry taking A to B, you mean that the first thing goes to the first thing, the second one goes to the second, and so forth. Okay, so any plane satisfying the 10 axioms, actually I say a plane, but it's really a set and distance satisfying the 10 axioms Euclidean plane. So let's look at the plane. I'm not going to write all the axioms out because it's not too exciting, but some of them are sort of basic things, like any 2 points determine a unique line. And a non-triviality axiom that there exist 3 points that are not collinear. And then the triangle inequality. But notice here we want the strict triangle inequality. If the points are not, if they are on a straight line, this is equality. But if they're not, then it should be strictly less. This will come up a little later. And a circle intersects every ray from the circle or inside the circle going outside. This is a topological axiom. It has to do with the completeness of the circle. Okay, so you couldn't, for example, have only rational points on the circle because it wouldn't have this property. John Baldwin and others have investigated the topological properties of completeness or of continuity and completeness from this sort of axiom, but we're not going there. We're going to use the real numbers. And then there's the famous parallel postulate that if you take a point that's not on a line, then there's exactly one line through that point and parallel to the given line. Okay? You can actually assume there's at most one. Okay. And then there's 2 axioms that are different from the rest. The length measure axioms, or LM 1, 2, and 3, and 2 says that any 2 line segments that have the same length are congruent. Okay, now that says there's a whole lot of isometries. You take any 2 segments of length 1, there's supposed to be an isometry taking one to the other. This is a huge homogeneity assumption, and that's very strong. And the next axiom, Hilbert wanted to use side angle side, which is more basic, except you don't know what an angle is. You see, you only have distance measured. So all you can do is say that if you have 2 triangles and pairwise the sides are the same, but by the first thing, you really want to say not just the distance is the same, but that they're congruent. Okay, then offhand there could be 3 isometries taking one side to one, side 2 to side 2, side 3 to side 3. And in fact, the axiom is that there's one isometry which does all 3 at once. So these are 2 strong axioms, and they're going to come into play quite a lot. Okay, the rest of the axioms are really basic. So, okay, forget all that. Let's go to the vector norms. So last time you taught numerical analysis, the first thing you do about the second month is talk about vector norms. So a norm on a vector space is just a function, phi, which is positive and strictly positive. So it's phi of x is strictly greater than 0. If x is not equal to 0, phi of cx is the absolute value of c times the norm of x. And then it satisfies the triangle inequality. In order to make a strong norm, I need to add the strong triangle inequality, which corresponds to the axiom we saw earlier. So, for example, if your norm is the L1 norm or the L infinity norm, where the unit circle is a square, they don't satisfy this. Okay, they would have less than or equal to, but not less than. And now you get a distance function just by taking the distance between 2 points to be the norm of the vector between them. Okay, so for example, the standard norm is just the square root of x squared plus y squared for 2 points on the real plane. Okay, suppose instead of just the regular norm, you use one of these norms and assume that it's a strong norm. So a strong triangle inequality holds. Then the amazing thing is the points and lines are exactly the same points and lines that you're used to. In other words, y equals mx plus b, and then the vertical lines, x equals a constant, and that's it. Okay. So that would not be true if you used the L1 or the L infinity norm, and that's the reason we're throwing those out. And the unit circle is a strictly convex closed curve. Okay, so these are topologically the same as an ordinary plane, okay, but distances and angles are different, okay. And in fact, you can show that the strong triangle inequality is equivalent to the unit circle being strictly convex. Okay, so here's an example. This is a normal vector norm. Instead of square root of x squared plus y squared, we add a term, square root of x squared plus the absolute value of xy plus y squared. And the unit circle looks like this. And if you look at that, well, it's not a circle, it's not round. It is a strictly convex curve. And in fact, it's, in this case, differentiable at most points, except at these vertices here. Okay, and that's the sort of thing we're talking about. Okay. There's actually a converse. You take any function and you write in polar coordinates, r is h of theta, and it has to be that for a vector norm, phi of x is the same as phi of minus x. Okay, so you need that h of theta plus pi is h of theta. Then, in fact, that gives you the unit circle for some vector norm. Okay, so it's really quite general. Okay, we're going to be interested in the isometry group. Okay, the isometry group of a norm plane. So again, the real numbers with a vector norm determining the distance. It's a semi-direct product. Okay, so in other words, you have the normal subgroup of all isometries that fix the origin. Remember, the points and lines are the same as they ever were. Okay, and then you have the group of all translations. Obviously, an isometry for any vector norm. Okay, and so in the Euclidean case, the normal subgroup fixing the origin would be all 2 by 2 matrices with determinant plus or minus 1. Plus 1 gives you rotations, minus 1 gives you reflections. Okay, so you have all rotations, reflections around the origin, and then if you want to do a rotation reflection elsewhere, you have to do a translation. Okay, so for the standard plane, that's what they would be. But for any plane, you still have the semi-direct product. Okay, again, and semi-direct product just means that the join is all isometries. Every isometry can be written as a product of a translation and a rotational reflection. Okay. So let's look at four types of planes. We can look at the planes that are defined by the axioms, or we can look at elliptic planes. So planes where instead of just x squared plus y squared under the square root sign, you have a quadratic, positive definite quadratic form, ax squared plus bxy plus cy squared. And of course, you need to be positive definite. That is, you need that b squared minus 4ac is negative, as I've written the other way. And so that's the second kind of plane. Third kind of plane would be to use the other norms. Now, when you're teaching numerical analysis, you always use the norms with 1, 2, and infinity, but you can use other norms. So let's look at the LP norm with p an integer bigger than 2. Okay, so these give us another source of examples. And then we need some way to mess up the isometries. And the easiest way to do that is to add the absolute value of x to one of the previous norms. Okay, and that will reduce the symmetries of the plane in ways that will be predictable. Okay, so let's look at those four types. That's not all there are, but this provides us with a large source of examples. Okay, Euclidean planes, you remember from high school. This is the waterfall Lemmy was going to look at. And it's really isolated. Nobody knows this trail. You have to crawl on all fours to get there. And but it's a pretty waterfall once you do. Okay. But I'm not going to review high school geometry. That you learn in Miss Faust's class. Miss Faust, as best I could tell, was a contemporary of Euclid. She was ancient, but she did make you write geometric proofs, and that was a good class. We have elliptic norms, and elliptic norms are called elliptic because its circle is an ellipse. Okay. No surprise there, again, from Calculus 3 and analytic geometry. So here's one example. If you just take x squared plus 2y squared, then you get an ellipse like this. And if you take something different, so this is actually x plus y squared, then you get still an ellipse, but now it's tilted because of the xy term. Okay, but you learn how to put those in standard form in Calculus 3. Or better yet, go to linear algebra class and you learn that a positive definite symmetric real matrix is orthogonally diagonalizable. Okay, and therefore it has a square root because the eigenvalues are positive. And it turns out that every elliptic plane is just the plane given by an inner product, but the inner product is thinking of the vectors as column vectors, x transpose my, where m is the sandwich matrix, and that should be a positive definite symmetric, in our case, 2 by 2 matrix. So for example, for the Hilbert norm, we had x squared plus 2xy plus 2y squared. And there's a matrix. Okay, of course, the 2xy is split between the xy and the yx terms. But otherwise, that's it. And of course, this is a positive definite symmetric matrix. Now, finally, we get the Pythagorean theorem. What does Pythagorean theorem say? Pythagorean theorem says if the dot product of two vectors is 0, then the xy and yx terms, are missing from x plus y times x plus y, or x minus y and x minus y, and you get xx plus yy. In other words, x plus y squared is the norm of x squared plus the norm of y squared. This holds for any elliptic plane because the inner product just is standard inner product with a sandwich matrix that's a positive definite 2 by 2 matrix. Okay. So in fact, one of our main results is the following characterization of Euclidean planes. So the following are equivalent for a strongly normed plane on the real numbers. Again, I'm using the real numbers now and not an arbitrary Euclidean plane. One is the two axioms we discussed, the one that segments of the same length are congruent, and the side axiom for triangles. Then second is it's isomorphic to the standard plane. And the third equivalence would be that it's elliptic. In other words, the distance is given by a positive definite quadratic form. Okay, ax squared plus bxy plus cy squared, the square root of that. Okay, and the third is that it's the norm is an inner product because the inner product is just determined by the sandwich matrix. Then one of my favorite theorems from linear algebra second semester is that this is equivalent to the parallelogram law. That if you take two vectors and then you look at the norm of x plus y squared and the norm of x minus y squared, you get twice the norm of x plus the norm of twice the norm of y. Okay, this is not trivial. Okay, but it's in a lot of advanced linear algebra books. I use DIM, DYM, which is a really classic text. And then, as to what we're doing here, the equivalence would be that the orthogonality relation is symmetric. If you have two lines and K is perpendicular to L, then L is perpendicular to K. That does not hold in all norm planes. Okay, and notice we use that in the proof of this Pythagorean theorem, the second proof, and that all right angles are congruent. That is, all right angles are the same. Again, that's a non-trivial theorem of Euclidean geometry, and it doesn't have to hold in all planes. So we're going to pursue non-Euclidean planes, concentrating mostly on the last one. Okay, so I said we're going to do three kinds of examples. We said that the Euclidean planes given by the axioms are the same as the elliptic planes. So let's go to the norms that are not elliptic. And the obvious thing would be to look at an LP norm, a standard norm. And so here, for example, is the unit circle for the L3 norm. Okay, it's looks, as we said, it is a strictly convex unit circle, so it's a strong norm. Okay, and by the way, how do you check convexity? Because I've checked many examples. You've got to use the Hessian matrix. Okay, that's from calculus 3 also, so no problem, except if you do second derivatives and so forth. Okay. So we look at the plane. So P sub n. So for example, P sub 3 with the L3 norm, and you have all the translations are isometries. Okay, but there are only 8 rotations and reflections. Okay, now if you look at the norm, just going back, x cubed plus y cubed, obviously you can interchange x and plus and minus x, and you interchange x and y. Okay, but it turns out that's all you can do. Okay, and that gives you a dihedral group. Okay, xy goes to plus or minus x plus or minus y, or plus or minus y plus or minus x. So an 8-element group. And when I talk about D4, I'm going to mean this group of translations. Okay, these are the matrices with determinant 1. These are the matrices with determinant. Well, it depends. Sorry, that's not quite true. But the determinant will be plus or minus 1 for these. Okay, and we look at these planes. So the big idea was that these would relate these to the axioms. Well, the trouble is they fail both axioms. So remember, the two axioms characterizing a Euclidean plane are that line segments of the same length are have an isometry taking one to the other, and that if your two triangles the sides are congruent, then there's an isometry taking one triangle to the other. Both those axioms fail. Okay, so as you can guess, this is the initial look to find the independence of the axioms. Okay, so here, let's go to the fourth type of plane where we add the absolute value of x. Okay, so this is what I call xi or xi2, where you take the absolute value of x plus the square root of x squared plus y squared. Again, unit circle looks like this. It's nice. It's not round, of course, but it's a strongly convex plane. And now what we've done with the plus absolute value of x is you can do x, y goes to plus or minus x plus or minus y, but not plus or minus y plus or minus x. You've destroyed that. Okay. So the isometry group still has all the translations, but now there's only 4 rotations and reflections fixing the origin. And it turns out that the side axiom works. Okay, simply because they're not isometries to fool with. Okay, and it's almost an accident that it works, but it's because there's not enough isometries. Okay, and so whenever you take the absolute value of x plus an LP norm, you have this, an axiom, a geometry that satisfies everything, okay, except that line segments of the same length are not congruent. In particular, that shows that this axiom is independent. Now, that leaves, by the way, the rest of the axiom has been shown to be independent, except one of the early ones is not. But the authors of the book know that. Discovered it soon after publication. Okay, and we don't know whether or not the side axiom is independent. David Clark, and I've been emailing him quite a bit, has some ideas of how we might prove that's independent, but we don't know. Okay, so that's where that stands. So let's look at how right angles work. We've shown that, and here's the basic facts. Euclidean planes or inner product spaces, 2 parallel, non-parallel lines, define K to be perpendicular to L if the closest point is intersection. I'll have a picture in a second. Okay, and the following hold a Euclidean plane. Perpendicularity is symmetric. It's a relation between lines, and orthogonal lines meet in 4 right angles. Well, you can do a right angle. and or 8 if you count the order of the angle. And now, then two non-trivial theorems from Euclidean geometry is that an angle congruent to a right angle is a right angle, and all right angles are congruent. Okay. Using the last two, in Clark and Pathania, it's shown how to define angle measure. Notice we have not talked about angle measure, only distance measure. And so you can define angle measure and so that angle measures are congruent so that they have the same degree measure. You can also define area measure, which I've carefully avoided. Okay, so let's look at this. Let's look at two lines. The first would be y equals mx, and the second would be y equals nx. And you want to know whether if you take a point on one line, what's the closest point? Okay, well, intuitively, the closest point is you drop a perpendicular to the second line and you solve for it, and you get the intersection point at the perpendicular. If this were an acute angle, you get a different point. Okay. More generally, if phi, your distance function, is not the square root of x squared plus y squared, this is a calculus problem. Same sort of calculus problem you've assigned to lots of times, right? Here's a point, AMA, find the closest point on x in x to this point. And it's the same thing as dropping a perpendicular. Okay, so it's just a calculus problem. And the trouble is, when you go back from here to there, it doesn't have to be the same point. Okay, if this is the closest point, it doesn't mean that is. So let's do some straightforward examples. Okay, so let's look at the LP norm. Now, I'm using P here, and sort of make a table of what's orthogonal to what. So we have the vertical line, x equals 0, that's the y-axis, and you got the horizontal axis, and you look at y equals mx and then take a different y equals nx, okay? And here we see that the axes are perpendicular, okay? They're not perpendicular to anything else. And now, if P was 2, when are two lines perpendicular? It's when m times n equals -1. M is -1 over n. Okay, so great. That's a symmetric relation, and it's no problem. If you take P equal to 2, okay, it's when m and n is negative, but m squared n is 1. That's not symmetric, right? And that's where it screws up. And of course, if P is anything except 1, it doesn't work. So when P is bigger than 2, you get the lines y equals plus or minus x, because if m and n are plus and minus 1, of course this holds. And the axes are perpendicular, but nothing else is. Okay, and remember, this is a common ordinary norm which we use. Okay. Now let's go to this norm with the psi norm, which we use here. And we see that the y-axis, x equals 0, is perpendicular to y equal nx if n squared is less than or equal to 1. This is not normal behavior. I mean, you don't get a whole bunch of perpendicular lines. And of course, it's not symmetric. The only mutual orthogonal pairs are the origin and the y is plus or minus the square root of 3x. The square root of 3 comes from this thing. If you stick in the square root of 3, you get minus the square root of 3. Okay, you can see that pretty easily. Okay, if you stick in minus the square root of 3, you get the square root of 3. But otherwise, it's not symmetric. Okay, so you have to decide what you mean by a right angle. Okay, there are two possible definitions. One, the most natural one, is to simply say if K is perpendicular to L and L is perpendicular to K, then the angles at the intersection are right angles. A second possible definition, which I've not fully explored, is to use the parallelogram law, but it's strictly stronger than this. Okay. And the trouble is, right angles need not be congruent. And what's worse is that PQR and RQP don't have to be congruent. In other words, you have to distinguish between plus alpha and minus alpha. So let's use this notation to do an ordered pair of rays. Okay. So, for example, here's the coordinate axes. There's actually 8 angles here. Okay. Opposite angles are always congruent, but there's no reason that from I to J is the same as from J to I. Right? One is plus 90 degrees, the other is minus 90 degrees, if you will, and those are not the same. Okay, now I can't use 90 degrees, that's cheating, but there's really 8 angles here, and pairwise, they're congruent, but that leaves you 4 congruence classes. Now, the side version, we can now write in the following way. Okay, you take 2 triangles where the PQ sides are the same and the QR sides are the same, and the ordered angles are congruent, then in fact, the last side is the same. Okay, and that's almost a triviality. Okay, let's look at our famous norm here. So this norm here, we look at 2 triangles. This is a right angle at the origin. And you take 2 triangles, sides 1 and 2, but the hypotenuse is not the same. The hypotenuse is not the same because these angles are not congruent, because plus 90 degrees is not the same as minus 90 degrees in this plane. Okay, now not the same, I mean not congruent. Okay, this sort of messes with the Pythagorean theorem immensely. Okay, so let's say the PT property is that for a right triangle, okay, that is when the 2 short sides are perpendicular, that determines the hypotenuse. So that's the Pythagorean property. Okay, and now in the Euclidean plane, all right angles are congruent. Okay, that is, there's a right, for any 2 right angles, there's an isometry taking one to the other. And this is just repeating the previous property. And so we get the Pythagorean in the following form. If you have a plane with the property that all right angles are congruent, then it has the Pythagorean property. Okay, not a squared plus b squared equals c squared, but that the 2 short sides of a right triangle determine the long side. Okay. This, by the way, I'm showing you various hiking. I had to crawl on all 4s up a pig trail to get this view. That's the reason I put this slide in. So, so in an elliptic plane, it looks like you expect. A squared plus b squared is c squared because we said the Pythagorean theorem holds. What doesn't hold is that 90 degrees is the same thing as a right angle. Okay. Okay. This angle here, which is, I don't know how many degrees it is, but it's not a right angle in the terms of standard normal measure. These 2 things do not have mn equal minus 1, but they're orthogonal in the sense of the shortest distance. Okay, so this is just with the weighted norm. Here's one with the Hilbert norm. Again, the two short sides determine the hypotenuse, but notice the hypotenuse is this side, not that side. Okay, in fact, you can slide this over to there, and you see that these two are right angles and this one ain't. So it's sort of surprising. Now, you also see that the right angles add up to a straight line, which is sort of neat. Okay. Now, an option, if not all right angles are congruent, is to break the right angles up into congruence classes. All triangles whose right angles, all right triangles whose right angles are congruent satisfy the same identity. Okay, now it looks a little weird. Okay, so, but let's just look at an example. Okay, so P4, the norm is the fourth root of x to the fourth plus y to the fourth, standard norm. There are two sets of right angles, those that are parallel to the axes. Those satisfy a to the fourth plus b to the fourth is c to the fourth. Then you got those that have plus and minus x for the right triangle, and they satisfied c to the fourth, a to the fourth plus b to the fourth plus 6a squared b squared. So the Pythagorean theorem actually has two forms. Okay, one for each congruence class. It turns out that if the isometry group has exactly those 8 congruences, then there's two classes of right angles. The right angles, those are plus or minus x in the congruence class, and they have different angles. So you don't need the fourth power. Anything with this isometry group works. Okay. Now let's look at this plane. This plane, there's 4 isometries. If you look at the intersection of 2 lines, there's 8 angles, if you count plus and minus x different. Now, here's combinatorics. If there's 4 isometries and there's 8 angles, by the pigeonhole principle, they're not all congruent. And so, in fact, that's what we saw. Okay. There's 8 angles, counting plus and minus x is different at the origin, but they're not congruent, and the formulas for the right triangle are different. The same formula for each congruence class of right angles, but different congruence classes have different formulas. Okay, and then there's another set of formulas for plus and minus the square root of 3x. Okay, which is the other set of orthogonal things. Okay, so the basic conclusion is that if you're given a strong vector norm, you can construct a plane, okay, where the straight lines are exactly the same as you're used to, y equals mx plus b in the vertical lines, okay? If that norm is an elliptic norm, you get a Euclidean plane and all the axioms, and conversely. If not, then you get a different sort of plane, okay? And it could have actually as few as 2 isometries. I can't find one with none yet, okay? And the Pythagorean theorem is a side angle side theorem, but for different isometry classes of right angles. Okay, here's the problem is there a non-Euclidean plane in which all right angles are congruent? Because that would mean the Pythagorean theorem does not imply Euclidean. In particular, is there a strongly normed plane with no right angles? I cannot find one. I've tried all sorts of things, and thorny problem. And in fact, the closest we have is the equivalence we already said. If orthogonality is symmetric, and if all angles are congruent, then it's Euclidean. So that's if and only if. But we don't know about other non-Euclidean planes. So I want to thank you. I want to also thank David Clark for a number of interesting email conversation and his guidance on this problem, without which none of it would have happened. Besides the wonderful book, which you should go buy, he's pointed me the right direction several times. Okay, so, and thank you for listening. So,
any questions?
So is it already published somewhere? Like you posted it? Did you post it?
yeah, it's on my website. Of course, the paper with the proofs is considerably longer and has other examples. But it's math.ly, or you can just Google me and go to the paper section of my publications. And so it's a preprint there. And the nice thing is, while the results are non-trivial, almost nothing is used beyond what you teach in undergraduate mathematics, right? At least if you get lucky enough to teach an advanced linear algebra and numerical analysis course. But some of it's calculus 3 and calculus 1.
So how much is of what you presented is actually in this book that you mentioned of 2023? So this,
how much?
So how much of this variety of planes is actually explained in the book that you mentioned?
Oh, the book primarily focuses on developing the Euclidean case strictly axiomatically, okay? And a large portion of the book is spent in three things: developing area measure, okay? Of course, we intuitively do an area measure, and that's good enough for you and me, but it's not good enough for a real geometer, okay? Angle measure, okay, which sort of screwed up Hilbert, but that's developed fine. And then the wonderful coordination theorem, think of the coordination theorems of von Neumann and others, that any Euclidean plane, in fact, is just an inner product space. And that's certainly highly non-trivial. And in fact, there are uncountably many models where you take a countable Euclidean field. So I didn't go there at all. I used the real numbers, but there are uncountably many models, but they differ by being Euclidean spaces over different fields, different real fields. So yeah, there's a lot of deep stuff in the book, and there's 5 proofs of the Pythagorean theorem. Okay, and only the last one I think uses area measure. You think of it as an area idea, but it's really not. So it's a more basic, in some sense, relation.
Anything else? All right. Let's thank the speaker again.
And thank you for this opportunity.
Of course, yeah. I'm going to stop the recording now.